we are learning this chapter 6. This chapter is about the data link layer and local area networks. In terms of the TCP/IP protocol suite, 5 protocol stack, this one is second layer. We just stepped down from the top layer application and later transport layer. Then we just learned about and completed network layer. And this is the data link layer, second layer. This chapter is explaining about the link layer and LANs. Our main goals are to understand the principles behind the link layer services. Those services are error detection and correction. But we are mainly using this error detection instead of correction. And also this service about sharing a broadcast channel, that is multiple access scheme we learn. And the link layer addressing, also we learn about that. And we learn about this protocol, Ethernet, that is mainly for local area networks. And the virtual local area network concept, we learn about that. And instantiation, example, and implementation of various link layer technologies. We learn about them in this chapter. This chapter is composed of these 7 sub-chapters. First one is about introduction and the services. Second sub-chapter, 6.2 is explain about error detection mainly, and some about the correction. And 6.3 sub-chapter will explain about the multiple access protocols. And 6.4 that will explain about LANs and addressing scheme, also protocol, address resolution protocol. And some Ethernet concept and technology that will be explained. And about switches, also virtual LANs, those are explained in this subchapter. And 6.5, this subchapter will explain about link virtualization. Multi-protocol label switching, we learn about this one. And after that, we learn about data center networking, how the data center is using this networking, and some concept about the data center configuration. We learn about that. And finally, we learn about this example, a day in the life of a web request. And we'll finalize and complete this chapter. Also, we'll complete this semester. Okay, let's move to the next. Okay, this one is about the link layer context. As we learned already, datagram that is transferred by different link protocols over different links. And we learned this one, the datagrams from network layer that will be transferred by different link protocols over different links. Think about that datagram from the network layer that will be transferred through this data link layer. This is the example for that. Ethernet 1 first link, frame relay 1 intermediate links, and if we are considering the frame in this data link layer, we are calling that packet from the datagram in the network layer. That will be changed to frame, Ethernet frame. In that sense, we can think that is frame relay on immediate links. And many Ethernet related technologies are being used for Wi-Fi, for example, 802.11, ABG, and so on. Each link protocol provides different services. For example, may or may not provide reliable data transfer over link, and we can use the physical line, or we can use simply the radio channel, that is wireless. like Wi-Fi. And we can think this transportation analogy to understand better using this analogous example. Think about one trip from Princeton to Lausanne in Swiss. Probably this also is living in this Princeton, in that area, and he is using limousine to travel from Princeton to John F. Kennedy Airport. And from John F. Kennedy Airport, International Airport, to Geneva, that will be using this airplane. And after arriving there, Geneva, train will be used from Geneva to Lausanne. This is the transportation analogy, and we can match to our terminology in computer network, especially in this link layer. Tourist. This one is like datagram in our link layer and in our computer network terminology. Transport segment, that is communication link. And transportation mode, that is like link layer protocol. We are using highway, and we are using this limousine on the highway, and the airplane and train. Those will be used for each different link layer. Thus that this relate to that link layer protocol. Then how about the routing algorithm in our computer network terminology? That can be this one, travel agent. Travel agent is planning and provide some planned information to us as a customer. Then that information will be efficient or effective, and that is similar or analogous example to our routing algorithm in computer network terminology. Let's look at these link layer services. What kind of services provide in this link layer? First, framing and link access. With this one, we can encapsulate datagram into frame. Think about that datagram from the network layer to send through the physical link. Before that, we are using this Ethernet link, that is data link layer. And here we are encapsulating this datagram into frame. Thus we are calling the packet as new terminology frame. Adding header and the trailer. We learn about that Ethernet frame format later. Also, you can observe this one with your Wireshark. Then you can observe that header and the trailer also. And the channel access. If we are using shared medium, then how we can access the channel. There is some protocol, those we learn about that, to access the link. And here we are using another address scheme, that is media access control address or physical address. If we are using Ethernet, then that is called Ethernet address, used in frame headers to identify source or destination. That is different from IP address. This is 32-bit in our IP version 4 addressing scheme. If we are considering Ethernet, then MAC address or physical address or Ethernet address, that is using 48-bit, that is 6 bytes. This IP version 4 is using 4 bytes per address, but here 6 bytes. We learn this one later also. Also, this link layer is providing this service, reliable delivery between adjacent nodes. Mainly, that adjacent nodes, that link is being considered for reliable delivery. And also, we learned a little bit about this concept already in the previous chapter. And If we are using fiber optic link instead of twisted pair link, then low error bit link that will provide low bit error link. Fiber optic link is providing that. Wireless links, think about Wi-Fi. That is very in high error rates. And why? Both link level and end-to-end reliability, we are requiring them. This link level reliability is provided by this data link layer, and end-to-end reliability that is provided at the post layer, transport layer. Why we need both of them? We should provide the error-free communication. If we are using UDP, then that is not providing that reliability. In that case, we rely upon only this link level, data link layer, to make sure anyhow to provide that error-free data to the application layer. We need lower layer here, data link level, and also in the transport layer. Here we are verifying that error-free data. A little bit more about the services in link layer. Let's look at this one first. Flow control. This one is different flow control from the previous transport layer, and this one is mainly for pacing between adjacent sending and receiving nodes. Think about our computer and some router between them, then link, physical link. And also between switch, we should try to match the speed. That is the adjacent nodes. One is sending node and another one is receiving node. They are attached using the single link, and we are considering that flow control in that link. That is link layer service, one of the link layer services. And error detection, we need this one to make sure that error-free data. Errors caused by signal attenuation or noise. Depending upon the electrical characteristics, errors are always occurring, and we should verify. Thus, we need to detect that error. Receiver detects presence of errors. Signals send for retransmission or drops frame. In that case, if that error is detected by the receiver, then inform sender about that error and request that retransmission. If that is containing error, that frame is containing error, then that frame will be dropped and thrown away. And another more advanced functionality, that is about this error correction. Usually we are not using this error correction, but conceptually, if we are using this functionality, then that is belonging to this link layer service. Okay, this one is doing this. Receiver identifies and corrects bit errors without resorting to retransmission. That means without retransmission, receiver can correct that error frame. Okay, this one can be used in special situation, but usually in our Ethernet, we are not using this scheme. And we have a different communication mode. One is half duplex, full duplex, another one is simplex. Usually broadcasting, like radio channel broadcasting and the TV channel broadcasting, that FM signal, AM signal, those are being broadcasted, and that is called simplex, one direction. But think about the walkie-talkie. using wireless communication device. Then it is using half-duplex. That is doing in this way. Nodes at both ends of link can transmit, but not at the same time. Only one node can send, not at the same time. And after finishing one node's communication, then the other node can communicate, can send, can transmit. But if we are considering our telephone or even our computer communication, when we are sending at the time, simultaneously we can receive. Think about some analogous example. On the highway, one direction and another direction, we can go, and the another direction, another cars can drive at the same time. That is called full duplex. And our telephone communication is based on this mainly. Full duplex. Where's the link layer implemented? Then we can think where the link layer is implemented. That will be implemented in each and every host. Does this computer or router, switch, we can think that, and we can see that examples later. In each and every host, link layer implemented in adapter, also known as network interface card. Long time ago, we used this different adapter card separated, but notebook and current computers are embedded. Those are embedded in this same and single motherboard. But a long time ago, that was using different adapter card. Thus, we should put in our system bus. Ethernet card, 8.11, ABGN, those are different version of Wi-Fi. And Ethernet chipset, those hardware can be used. And this network interface card, or this one, implements link and physical layer. Those link layer and the physical layers are those are usually tightly integrated, attaches into host systems buses. If we can see this physical thing, then that is physical layer related. Above that, logically, we are using some functionality. That is link layer functionality. And combination of hardware, software, firmware. Usually that software firmly programmed there. That is called firmware. And our Ethernet controller program is firmly stored there. So in some memory, read-only memory, or programmable read-only memory, then that is called firmware. There's that link layer functionality is embedded there. And in terms of the layered scheme, this is the link layer, and this controller and the physical layer. Think about Ethernet cable. Those are implemented here. Okay, let's move to the next. Then how adapters are communicating. Here, controller and some physical interface chipset, Ethernet, physical interface, to send and receive signal, and this packet here mainly that is called frame. This datagram is called frame here in this link layer. Sending side, this one is encapsulating datagram in frame, and that is error checking bit. This one is checking error, and the result will be added mainly for error checking, and reliable data transfer and flow control between this and this to match the speed, to pace up. And receiving side, this one is looking for that errors, whether there is any error, depending upon some error checking bit that is comparing. We'll learn this one later. And the reliable data transfer only between this one and this. And flow control only between this and this. That flow control is not end to end. This is this node and this node, only in this link. And after that, extracting that datagram for third layer and pass it to upper layer at receiving side. Okay, this one is explaining about error detection mainly, a little bit about correction. Error detection first mainly. Here, let's look at this acronym, that is EDC. EDC means error detection and correction bits. That is redundant one, mainly for error checking, error detecting, error detection and correction. And these data, original data protected by error checking, may include header fields. Even though we are detecting errors, that error detection may not be 100% reliable. Protocol may miss some errors, even though that is rare case. If we are using large EDC field, then that will be better detection and correction. Think about this datagram from the network layer, and that will be here in this link layer, that will be used to calculate this EDC. We'll use this method, how this one can be calculated and attached here. And this original data and this EDC for error checking, error detection, and correction if we are using correction scheme, but mainly we are using error detection. Thus, this one is mainly for error detection, and that will be sent through this link. And that will be arrived to this adjacent node. Then this one may be corrupted if there is any error. And also this one is using this EDC, arrived one. Also this may be corrupted, but we are using this one to compare. Here we are calculating with the same algorithm the different EDC here, and that EDC and that EDC dash this one will be compared together. All bits in D okay, that is okay, then not okay, then there's some error. If that is no problem, no error, then that will be sent to upper layer. That means network layer. And the datagram, that is the data here, that will be transferred to the upper layer, network layer. Most primitive and old one is parity checking. This one is introduced here, even though we are not using in our computer network. This one is used usually in the modem, very low speed modem like a 2400 or 9600 modem. this one may be used. Why? Between, in most cases, between this dumb terminal and the main computer, and if we are using the monitor and the terminal, then that is called dumb terminal, and this very simple parity checking scheme was used. We may use this one or not. There may be even parity or odd parity. We can choose using the terminal. Long time ago, when we are using IBM mainframe computer, time shared machine, and we used many monitors, terminals to use based on time sharing. And between this dumb terminal and the computer, we may use this parity checking depending upon our setup configuration. We may choose no parity checking or even parity or odd parity checking. We can choose. Let's look at this basic explanation about this. Single bit parity. This one is detecting single bit error. If we are using this bit, this is called parity bit, and this one is the original data. To check some error, we are using this parity bit. This parity bit, if we are using two-dimensional bit parity, then we can check in this way, also in that way. Then that is called two-dimensional bit parity. And we can detect and correct the single bit errors. Let's look at this parity checking. This parity checking is being used between dumb terminal and some computer. A long time ago, we used dumb terminal to access computer. In that case, the distance is not long, thus the error is not happening so much. Also, the speed is like 9600 or twice of that speed. The error checking scheme is not complicated. This is very simple error checking scheme based on parity checking. Here, think about this data. And this parity bit is, if we are using even parity, then including this, the number of 1. Here, number 1 is how much? How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. Then this one is 9. 9 is even, 9 is odd number. And this one is 0, then that is total number of 1s, including this. That is odd number. Then we are using odd parity scheme. We can set even parity or odd parity. Here we are using probably even parity, and the data is simpler than this. Let's look at this one, 10101. That is original data, and we are attaching this one. This is parity bit. To make the number of 1, here 1, 2, 3, and that is odd number. Thus, if we are using 1 here, then that is 4 in terms of the number of 1s. 1, 2, 3, 4. Then that is 4 is even number. And this one is already 4 even number, thus that should be 0 if we are using even parity scheme. This one is 1 3 times 1, then 1 here, then 4 number of 1s we are using, thus this one should be 1. Thus we are using here even parity. Also in this direction, 2 or that is even number. Also this one is 1 and another 1, 2, and here 1, 2, 3, 3, 1 number of 1 here. Thus, if we are using 1 here, then how many 1s here? 1, 2, 3, 4. That is even number. Already this one is 2, thus that is even number. Thus we don't need to use 1 here. Instead we are using 0 here, 1. Thus odd number. Thus to make it even number we are using 1. This is parity bit here. Also this one is a parity bit, 2-dimensional bit parity. And that will be sent through that communication link, and that will be arrived in the destination node or adjacent node. Then that will be checked. If that is containing some error, then that will be corrected in this way. Okay, here checking. Okay, 0, that is correct. Okay, here just 1. Number 1 is just 1. That is odd number. Then that's wrong here. Thus this line is wrong. Which one is in error? We don't know. But okay, this one is correct. And also horizontally we can check. This one is correct. This one is something wrong here. 1, 2, 3. That is odd number. All lines should be even number of ones. That should contain even number of ones. Thus this one is wrong. Thus we can find out this one is being changed. Thus we can change it back. Thus if this one is change it back, then 1, then we can correct this one. This is very simple primitive example of error correction. But usually we are not using in our Ethernet and in our scheme we are not using this one. Thus this one is mainly for reference. Okay, let's move to the next. Internet checksum, and this is just a review we learned already. To remind, goal is to detect errors. For example, flipped bits in transmitted packets not used at transport layer only, sender side and receiver side. We learned about this one already in transport layer, and this one is just for reviewing. Remind, sender is treating segment contents as sequence of 16-bit integers, as we learned already. And the checksum bit we are using addition of segment contents. And the sender puts checksum value into UDP checksum field or TCP checksum field, depending on our transport layer protocol. Receiver will compute checksum of received segment. Check if computed checksum equals checksum field value. There's no difference, then not same, not equal, then that will be containing some error. Thus error is detected. If the computed one and received one, the checksums are equal, that is okay, no error detected. But that is not 100% perfect, thus may be errors nonetheless. We are using this CRC. That acronym is popular one. That original full name is cyclic redundancy check. The algorithm is doing in this way, cyclic redundancy check. This scheme is more powerful error detecting scheme. And also we are generating that CRC error detection data bit. After calculating with this generator, we can get some value, and we'll look at this one first. Let's follow this procedure. Database, original data is here, binary data, binary number, and we are using some bit pattern to generate. Thus this is called generator. Goal is to choose our CRC bits, and this is remainder. After denominating that original data D, utility is G, and that will be explained later in next slide. And you don't need to worry about this one. Remainder, we are trying to get some remainder after denominating with this generator. The data, original data will be denominated with this generator G, and we can get some remainder, that is R. That is the CRC bit for error correction, error detection actually. And that scheme, CRC, that will be used in our Ethernet, 802.11 Wi-Fi, and even the previous ATM technology, we use this one. And here, the CRC is being standardized worldwide, depending upon that bit number, how many bits are being used. CRC 16-bit, CRC 32-bit, and we are using CRC 32 in our 802.11 Ethernet mainly, we will look at later. Here, let's assume this one is the original data bits to be sent, and we are calculating. This original data will be divided with the generator G, then the remainder, there's some remainder, then that will be used. And we are using 32-bit in our Ethernet, and that will be sent to the adjacent node or next node through that link, and that will be compared. In the adjacent node, that is recalculating into the received data, and that calculated newly that CRC bit and received CRC, they are compared. In terms of mathematical notation and formula, that can be represented in this way. But you don't need to worry about that, exclusive OR. And this one will be much better for understanding. Here, original data, let's assume that is simplified one. And if we are using this 4-bit, but actually we are using 32-bit generator in our Ethernet, then finally this one will be here, remainder, below this number. In our case, below this 32-bit number, 32-bit, another 32-bit, below this number, that will be here. And that value, that is the CRC bit, that will be sent for error detection. And we don't need to worry about that. Just we need this information, mainly for error detection. And this mathematically, that was represented in that way. If we are implementing in hardware, then we are using exclusive OR or in shift register, then simply we can calculate this one. Even though it may be very complicated to calculate that by ourselves, but if we are using hardware instead of software, then it is very straightforward to calculate that on. Just exclusive OR shift register, then we can calculate simply in very fast mode. We can calculate the remainder after dividing this one with this generator. That is the CRC for error detection, and we'll look at this one and some homework. After solving that, you can understand better. Okay, let's move to the next topic. Next topic about the multiple access protocols.